Yeah, in this video, I'm going to discuss about the reduction as well as the oxidation of alkynes, which has been pulled out from the degree first semester syllabus, that is chapter 5, Acyclic hydrocarbons. The whole chapter has been discussed on my YouTube channel. The details of this has been given under the description below. If you want to go through the entire chapter, do look at the description and do like, share, and subscribe my channel. Yeah, let's look at this reduction of alkynes now in detail. So, reduction is nothing but the addition of hydrogen. So, this is clear. So, the alkynes can be partially reduced to alkenes itself. That means it can be stopped at the alkene stage without reducing it further to the alkanes. So, the stereochemistry, that means it's a cis or the trans alkene which is formed, depends upon the reducing agents which are using here, depends upon the choice of the reducing agent you are making here. So whether it's a cis alkene or the trans alkene you want to produce depends upon the type of the reducing agent we are using here. There are mainly two types of reductions. The first one is the reductions with metal ammonia solutions, and the second one is the catalytic hydrogenation. So reduction with methyl ammonia solutions results in the formation of this transalkene. Stereochemistry is can be decided here, and this catalytic hydrogenation with Lindlar's catalyst helps in the formation of this cis alkane here. So depending upon the reducing agent we are using here, the stereochemistry of the product can be decided. Let's look at this reduction with methyl ammonia solutions. The first type of reduction. See, the reducing agent we are using here to produce the we are producing a trans alkene, as we can see here from this uh, C, and C here. So we are producing the trans alkene, and the reagent which are using here is the sodium or lithium, which is dissolved in an ammonia solvent. That is nothing but the liquid ammonia. So sodium or lithium in the presence of liquid ammonia will give you this trans alkene. See, this one is the same thing here. This is the trans alkene and sodamide, that is NaNH2. Is a side product here, and let's look at this mechanism now, how this is happening. So when we look at the mechanism of this, the first is the formation of this dianion formation is there in here. This is a dianion. This is a dianion formation. First, the electrons of this from the metal gets transferred to this one of the p orbitals. Then we can see that it's a two pi bonds here, so it's an easily reactive when compared to that of the alkanes because of the presence of this pi bond. And the second time electrons are again transferred to other p orbital and the other carbon atom, resulting in the formation of this one here, resulting in the formation of dianion here. This is a dianion. Um, uh, Two negative charges on two different carbon atoms here. So this can be arranged in a trans form or a cis form. But we know that the trans form is more stable because of the less steric hindrance here. So transform is more stable and is most preferred. And the major product which is formed is a trans alkene in the next step. When we hydrolyze this addition of the H plus here results in the formation of this trans alkene in this here. So trans alkene is the major product which is formed when we are using the reagent, that is sodium or lithium in ammonia. So trans alkene is the stereochemistry of the product which is formed when the reagent is sodium in the presence of liquid ammonia. Sodium or liquid lithium in the liquid ammonia. So the same thing is discussed here. Donates the sodium radical donates electron pair to one of the p orbitals, the carbon-carbon triple bond, and then the another sodium will donate the another pair of electrons to the other p orbital on the other carbon atom, resulting in the formation of this dianion here, resulting in the trans product, that is the trans alkene which is formed here. For example, when we see the examples of this anti-addition, that is a sodium with liquid ammonia, when we see this alkyne, that is 1 2 3 4, yeah, yeah, 4, 1 2 3 4 5 6 7 8 4 octine here. So the trans alkene is formed here. So this is arranged in a trans manner. This is a product which is formed here. Uh, and the same example, we can see this pH and CH3 on the attached to the triple bonded carbons. So the anti-product which is formed, this is the stereospecific reaction resulting in the anti-addition. So depends upon the reagent, as I already said this. So depending upon the reagent which is used or the catalyst which is used, we can produce an alkene here from an alkyne. So reactions between alkynes and catalysts are the common source of this alkenes formation. And we know that these alkynes are more reactive because of this presence of these two pi bonds here. It can be anti product which is formed, that's anti-addition product, or the syn addition product, depending upon the reagent and the catalyst which is being used here. So in catalytic hydrogenation, with the help of a Lindlar's catalyst here, we can produce a 6 product here. That means syn addition is taking place, so cis product is or cis alkene is formed here. So when we use generally this hydrogen in the presence of this palladium catalyst or platinum catalyst, complete reduction will take place. That is, the whole of this unsaturation is removed, resulting in the formation of this alkane here. But this can be stopped here. This complete hydrogenation can be stopped here. That is, with the help of this Lindlar's catalyst here. So it can be stopped in the alkene stage itself, resulting in the formation of this cis alkene. So what is this Lindlar's catalyst? Let's see what is this Lindlar's catalyst. This Lindlar's catalyst is nothing but has three components. That's a palladium, calcium carbonate, lead acetate, and quinoline. So this quinoline serves to prevent the complete hydrogenation of the alkyne into an alkene. So hydrogenation is an interruptible process involving a series of steps, but it can be stopped with the help of a catalyst. That's a modified catalyst. For example, this Lindlar's catalyst, which can be stopped at the alkene stage itself, resulting in the formation of this cis alkene here. Yeah, for example, when we take this Lindlar's catalyst here, hydrogenation will take place. This butane here, this one cis product is formed here, cis butene is formed here. So the stereochemistry, when we are using the Lindlar's catalyst, is a syn addition and the cis product is obtained here. Yes, when we say the mechanism of this, why cis product is formed is, on the surface of this catalyst, the hydrogen is absorbed. Firstly, this hydrogen is absorbed, and then this addition will take place from this on the surface of this catalyst from the same side of the molecule. So the hydrogen will get attached, the addition of this hydrogen to this alkyne will take place on the same side of the molecule. Therefore the same side of this is absorption of the hydrogen to this surface of the catalyst. This is a catalyst here, and then the addition is taking place from the same side of the molecule. So the cis alkene is produced. The cis alkene is the product which is seen here because the attachment of the hydrogens to the same side of the alkyne triple bond from the surface of the catalyst here. Because of the hydrogen which is absorbed to the catalyst, the addition of this hydrogen is taking place on the same side of the alkyne. So the cis alkene is produced here. So the stereochemistry when we are using this linear catalyst is syn addition. So in conclusion, we can say that when we are using this metal in the presence of liquid ammonia, that is sodium or lithium we are using here, we get a trans product, trans alkene. And when we are using this hydrogenation in the Lindlar's catalyst presence, we are getting the cis alkene. The stereochemistry is decided here. And one more thing here, is when we are using H2 in the presence of palladium or the platinum catalyst, the complete hydrogenation will take place, resulting in the formation of this alkane here. So when we take these examples of this here, for the cis and trans alkene to be formed in the presence of H2 or the palladium catalyst, the complete hydrogenation will take place, uh, resulting in the formation of an alkane here. So this is alkane, which is formed when we are using the H catalyst here, that is hydrogen in the presence of palladium or platinum catalyst. And when we are using this sodium in the presence of liquid ammonia solvent, we are getting a trans product. See, this is the stereochemistry here. So trans product is formed. Let's see, 1, 2, 3, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Carbon, carbon, carbon. So when we are using Lindlar's catalyst, we know that is a cis alkene. It is formed. This is a cis on the same side of the molecule. So stereochemistry is syn addition. So cis alkene here. So these are the examples of the reduction in the presence of different reagents. Now look at this oxidation of alkynes here. When we come to the oxidation of alkenes, it happens in the same way as it is as it is as it is with the case of the alkenes here. So here the potassium permanganate is used here as oxidizing agent, which oxidizes the alkynes into 1,2-diones and carboxylic acid. This again, the nature of the product which is formed, which is, that is whether it is diones which is formed or carboxylic acids, depends upon the reagent which are using here, or the conditions we are using here, mainly the conditions. Here the potassium permanganate is used here in the for the formation of this 1,2-diones. It is in the neutral conditions which is happening here. That is the KMNO4 is added in neutral conditions, and this one is in the basic or hot conditions here. So the carboxylic acid is produced when the oxidation is taking place in the presence of potassium permanganate under basic conditions, or when we are carrying out in the presence of heat here. Yes, when this oxidation is carried out in the presence of potassium permanganate under nearly the neutral conditions, then that's diketones is formed here. So neutral conditions, when oxidation followed by this hydrolysis will give you the hydroxylation here, the partial one, and here the complete hydroxylation with complete unsaturation is removed here in this case. So this is nothing but the tautomerism here. So tautomerism, that is a ketoenol tautomerism, or simply the tautomerism. Tautomerism will occur here, resulting in the formation of this product. How this ketoenol tautomerism is taking place is this is how the tautomerism is taking place by the shifting of these bonds here, like this, and this ketoenol tautomerism is being can be seen here. Yes, ketoenol tautomerism can be seen here. Yes, in the second case, where removal of this two water molecules here results in the formation of this dione here. Yes, O here, double bond O and double bond O, resulting in the formation of 1,2-dione here. When we are carrying out this oxidation in basic conditions or in warm conditions, this 1,2-diones which are formed here. Now this 1,2-diones are formed here, undergoes this oxidative cleavage. So the cleavage is happening here after the formation of these 1,2 diones, cleavage will takes place, resulting in the formation of the salts of carboxylic acids. This RCOO minus K plus, RCOO minus K plus, which on further treatment with free acids give you this carboxylic acids. And so in that case, we are getting the 1,2 diones. In this case, we are getting the carboxylic acids. Similarly, when terminal alkynes or this oxidatively cleaved in the presence of KMNO4, KOH, water, on further treatment with HCl will give you this carbon dioxide. This one, oxidative cleavage will take place, this RCOOH, and this is CO2 here because of this terminal alkyne here. And when this is cleaved, we get CH3COOH, CH3CH2COOH. There's two product which is formed here. And when this is cleaved, we get CH because this is CO2 because this is terminal alkyne. So this is used to know the position of the triple bond in alkynes. So this is generally used to determine the position of the triple bond in the alkynes. Now, let's say this ozonolysis. This is similar to the uh, potassium permanganate oxidation. This ozonolysis also, when ozonolysis followed by hydrolysis will give you this carboxylic acids here, to RCOH, R-COH and RCOH. And this one is CH3COH, CH3CH2COH. So this ozonolysis and oxidation in KMNO4 is used to know the or determine the position of the triple bond in the alkynes here.